Hi guys, welcome back to this Demystifying Machine Learning series. I'm Dr. Ganesh. We have been seeing different steps involved in the machine learning process and the different types of machine learning algorithms. So today we are going to see one of the very popular, famous fundamental algorithm called a support vector machine, SVM. So supervised learning models with associated learning algorithms that analyze data used for classification and regression analysis. SVM falls under this category. It can do both classification and regression. Given a set of training examples, each marked as belonging to one or the other two categories, an SVM training algorithm builds a model that assigns new examples to one category or the other, making it a non-probabilistic binary linear classifier. If you remember, naive Bayes was a probabilistic classification, whereas support vector machine is non-probabilistic classification. It's a representation of the examples as points in space mapped so that the examples of the separate categories are divided by a clear gap that is as wide as possible. New examples are then mapped onto that same space and predicted to belonging to a category. I'm sure it's not clear, so let me make it more complicated. Formally, SVM is a discriminative classifier formally defined by a separating hyperplane. Wow, what is that? So, in other words, given labeled training data, algorithm outputs an optimal hyperplane, a plane, which categorizes new examples. Still confusing, right? Don't worry, let's learn in layman terms. Suppose you are given plot of two label classes on a graph as shown in image A. Can you decide a separating line for these classes? Very easy. And this is exactly what SVM does. And this line is a hyperplane. In this example, it's a two-dimensional, but typically it could also be multi-dimensional. Let's make it a bit more complex. Now consider that if we had data as shown in this image below. Does a simple line segregate them properly? Quite tough, right? So in this case, we can separate them into another plane. So from the XY plot, we may change it to YZ plot, a third dimension, and a separation can be made, map it back, which will look like a circle in XY plane. Another way of SVM, doing SVM. Let's make it a little more complex. Now the data is little more uh, complicated, fluffy. So no matter how we put a line, except if we put a map of some country, it is going to have some error, some dots on the other side. So with lot of input data, we have to really check if we should really go for such a map or we should go for a straight line with some acceptable level of error. Often we go for this, a line with some acceptable amount of error, primarily because this is known as overfitting. When a new dot adds a black circle comes here, this is still going to be very tough, right? It's quite tough. So some key definitions. SVM algorithms help to find the best line or decision boundary, and this best boundary or region is called hyperplane. Clear, guys? Now, SVM algorithm finds the closest point of the lines from both the classes. These points are called support vectors. So you can see the support vector, an example here, one example here. The distance between the vectors of the hyperplane is called margin. So the distance between these two is called margin. And the goal of the SVM is to maximize this margin. How maximum this margin can be so that the line is the best. The hyperplane with the maximum margin is called as optimal hyperplane. Good versus bad margin. See here all sector vectors have same distance with the maximum margin hyperplane. Good one. A bad example is where one of them have a very huge margin and one is almost right next to that line. Similarly, there is also a concept of hard margin versus soft margin. The hard margin, as you can see here, does not allow the points to be between the margin, whereas soft margin allows some amount of points to be within the margin. And see here, because of which it is little more error prone. What about non-linear SVM? We have seen this example, but let's elaborate a bit more. If data is linearly arranged, then we can separate it by using a straight line. But for non-linear data, for example, consider this image. So we need to add one more dimension, as we mentioned before. So let's add a dimension z, and z is x square plus y square. So by adding the third dimension, it looks like this xc, it looks like this. So these points are now mapped into x versus x square plus y square. And then we are able to find a very good hyperplane. Now map it back to x and y, we get the best hyperplane. Here we get a circumference of radius 1 in case of non-linear data. Non-linearly separable data. See here, I have x and y. No matter, this line for example gives me an accuracy of 75% because this is correctly classified, incorrectly separated. So let's again do the same. We project it into, so if suppose x1 is xi square, x2 is x2 square, and x3 is root 2 x1 x2. We get something like this. We start with the above data set in the above figure, project it into a 3D with these new coordinates. You can see how it comes up. Thanks to KD Nuggets for giving such good visualizations. Now we are running SVM on it. Bingo, we have a perfect label separation. See here, wow. This, when we come back and map, we'll get a line like this as the boundary looks like this, and this is exactly what we want, and this gives 100% accuracy. So SVM works on the concept of kernels. In practice, SVM algorithm is implemented with kernel that transforms an input data space into the required form. SVM uses a technique called kernel trick, in which kernel takes a low dimensional input space, transform it into high dimensional space. In simple words, it converts non-separable problems into separable problems by adding more dimensions to it. It makes SVM very powerful, flexible, and accurate. Let's see some examples of kernels. Not everything, okay? Only two. It can be, so the simplest kernel is linear kernel. It can be used as a dot product between any two observations, which looks like this: kx comma xi is sum of x star xi. So we can see that the product between two vectors is the sum of the multiplications of each pair of input values. So linear kernel is used when the data is linearly separable. That is, it can be separated using a single line. Wide usage is on text classification. Each alphabet is a new feature. So another one is polynomial kernel, which is used for image processing. So for degree D polynomials, the polynomial kernel is defined as kx comma y equal to x transpose y plus e to the whole power d, where x and y are vectors in the input space, that is vectors of features computed from training or test examples, and c greater than or equal to 0 is a free parameter trade-off. The influence of higher order versus lower order terms is the polynomial. When c is 0, naturally the kernel is homogeneous. So in this video, we have seen an introduction to support vector machine. We saw linear support vector machines and non-linear SVM, how they works. We have seen a very brief introduction to the kernel trick and two different kernels, the linear kernel and the polynomial kernel. SVM is a lot more. I request you to go through various references I have mentioned in different slides to understand more. Let's see if we need a separate presentation later on. Thank you. Bye.